Okay, can. So let's start early, as in on time. Okay, so I'm gonna share screen. Okay, so what we are going to cover today is radiation, irradiance analysis. Okay, so this will be primarily the Ladybug command that we will be sharing with you. So what it does is that it calculates the incident radiation on the geometry using the sky matrix. Okay, and this is commonly used to approximate the energy that can be collected for PV cells. It is also useful for understanding how strong the sunlight is on the ground or on the facade. The first example that we'll be sharing with you will be how it's going to affect the ground. Okay, so that this will be very useful for you to use in your site analysis. Okay, so now what I want to tell you is essentially what's the difference between irradiation, irradiance. So you can understand irradiance is more skewed towards the solar industry, where it's calculating watts per square meter. Okay, which means the amount of energy per second. In the radiation analysis that we are doing over here, what the output will be is, let me scroll down, is in kilowatt hours per meter squared. So it's essentially the same, it's just that it is calculated by the hour. The values that you will receive will actually be to the cumulative of the period that you have set for your analysis. Okay, so now what you need for today's lesson is uploaded here. Under lesson 5. Okay, if you are not able to run this, that means you have to go back to this step whereby you need to install Radiance. Okay, so I guess most of you will already have the files, or you can quickly download the files now as I'm going through. So when you open up the file, there is a model.3dm. This is the Rhino file. And then this is the Grasshopper file. This one and this one. These two, we will begin with this first. So as you all are downloading and opening up the file, I'm just going to explain. So I've prepared this file so that it is easily usable for you to translate into your own design studio projects, be it architectural or landscape architectural projects. Because what I'm doing is an analysis on the ground. In terms of the overall overview of the grasshopper definition, my common workflow is that whatever that does something is on the right-hand side within this grasshopper canvas. Whatever that is an input will be on the left-hand side. So I find this useful for me, especially in my firm. So when I develop something, and my staff or interns want to play around with it, they can automatically know when they open this file that these are the parts where they have variables that they can input. And then if they're not confident, then they don't touch this part. Okay, so the inputs for this particular definition is that there is a analysis grid. So this is the extent to which you want to do your analysis, which is defined by a surface. And then we have the site context, which is what was already prepared for you as an example. Okay. Later on, I will share with you how to change this to your studio projects. If you recall, we have already done this in the last week, where we have show you how to go to the website to get the location of the EPW file, download it, and then import it. Okay. So what this definition does is that it will take a sky matrix. So you will create like a simulated sky, and then from there you will calculate the radiation. Okay, incident radiation. What I've also prepared for you, and which I find very important, is the orientation of the north. Okay, so you can see here, I've set up a system whereby if you were to rotate your north arrow, your radiation analysis will update itself accordingly. Because sometimes you may end up having situations whereby you are modeling your site in not a straightforward north y value being the north. Okay. So I guess most of you will have already have opened the file by now. Okay. But what we're going to do is we're going to do it from scratch. So now you just need to have this particular file, which is the Rhino file, open, model.3dm. If you have opened this, that's also good. You can use this as a reference. Okay, so now let's go and create a brand new file, file new document. Okay, so pan to the right. As I've mentioned, I want to be able to create my analysis surface. So I'm going to switch on my analysis surface. I switched it off because I wanted to play around with the visibility. So just double click on the canvas and create a surface. Okay, so by now this is week 5. This should come quite naturally to all of you. Clicking on the canvas, typing in and getting your commands and assigning them from the Rhino viewport. Okay, so just to be neat, I'm going to create a scribble to say that this is the analysis surface. Okay. So the next step that we need to do is we have to establish the B-reps. The B-reps are the boundary representations, which will be all of those meshing that we have modeled here. So right click, set multiple B-reps because we have 4 buildings there. And I can choose this, this, and this. Okay. So I'll just copy and paste this to annotate this accordingly. And this will be my site context. Okay. So now that we have these two, we're going to do the same step that we have done last week. Again, the way that I teach is it will always be a cumulative experience. So there will always be kind of like a little repeat overlap of what was done last week so that you have the muscle memory to remember what you need to do so that you can end up doing it by yourself next time. Okay, so you double click and type download EPW file. Otherwise, it is available here in Ladybug with this command here. Okay. And then the next one will be to import EPW file. Okay, so now connect this over to here. And naturally, we will need to use a panel, right? To key in our URL to this location. Okay, by now, most of your computers should have saved the location of the EPW map. Okay, or you can just type EPW map and Google it. The method that I showed you was to put in this grasshopper command, but you can also do it manually. Okay, so now let's just zoom. Whoa. Okay, maybe faster to just type Singapore. Okay, I'm gonna choose Alibaba now. Copy link to clipboard. Go back over here, double click, right click, paste. And okay. Okay. So now what we need to do is 2 steps. You have the sky matrix. So double click on the canvas and type sky matrix and choose LB cumulative sky matrix. So it needs the location. It needs the diffuse radiation here. And the direct radiation here. This portion is where you will input your analysis period, which we will come to later on. Okay. So what this is doing is that it's creating a sky matrix. What do we mean by sky matrix? So it's easy here for me to show you how it looks like. So just type dome, and there is a Ladybug sky dome here. Click on this. And now you connect this sky matrix to the sky matrix here. Immediately you will see something like this. So go to perspective view to look at it. Okay, so this is what the sky matrix is doing. You are visualizing the sky matrix now with this sky dome. So this shows you what the how the sun is moving across the sky throughout the year for Pi Leba, right? As a specific time interval for each of these squares. Okay, so it's like 45 for this square. Like the highest one will be like, I think it's around here, 45 kilowatts per Newton. Okay, so naturally that will also mean that ideally you should tilt your solar panels along this kind of orientation. Okay, it should never be flat. It should be always at a slight angle. Okay, so this is what we mean by the sky matrix. Okay. You can also set a point to show different kinds of to relocate where you want to put your sky matrix. For example, now it's blocking my entire what's that thing called? The site. So I'm just going to create a point. I can key in a new point here and put it here. So I've just moved it away. Okay. So now let's try to do the radiation analysis onto this particular surface now. So to do that, double click on the canvas again and type radiation. So I don't want the real-time incident radiation. So type incident radiation. Okay. So click on this over here. So what this needs is the sky matrix. And then it will need my materials here. So the geometry that I want to analyze and the context that I want to analyze. Okay. Now the important thing now is that you can see from here, it needs a grid size. And the offset distance is good to have. Irradiation is optional. The legend is optional because this is just to represent it. CPU count, we will come to this later on when we do butterfly next week. CPU count is useful when you need to do multi-threading. Okay, for radiation analysis, it will run quite quickly. And then, of course, we need a Boolean toggle to set the computer to run the analysis. So what should our grid size be? Okay, the units that I've set this up, in fact, for most analysis, you should always use meters, okay, instead of mm, because by default, they are set to meters. So it will go and think that your 3D file is all in meters. And if your site is modeled in mm, it's going to have like a 1,000 times more material to calculate, which is a common reason why a lot of people, when they first try to use butterfly, they get very discouraged because it takes a long time and they think that it's not very effective, but it's more often that they did not set the correct units. Okay, so having said that, right, I will want my grid size to be from between 1 to say maximum 5 meters. Okay, and I'm gonna put this over here. Okay, that's my grid size. The offset distance is the distance that is offset towards the inherent normal of the surface. Last week, we have shown you how you could, no, not last week. In the first few lessons where we were beginning to do the Esplanade tutorial, we were sharing with you how sometimes your sunshades will face downwards because of the way in which you have modeled the surface, and which is also because of the way that your U and V maps are being done. Similarly, this offset distance is going to be oriented according to where your normal is. So in terms of the values that we want to set for the offset distance, we always have to set it at least 0.1 meters, which is 10 cm above, 100 mm above the ground, right? It should not be on the same level as the ground. So I'm just going to put 0.1, less than 1, and it should not be more than 1 meter above the ground. Okay, why are there instances whereby I want it to be more than 0.1? That's because, for example, if you have a double curve, let me just draw a section of something that is double curve, right? When you have this, and it's offset in this manner, sometimes if it's too close to each other, they may intersect. Okay, so you have to tweak a fine balance between how much you want to offset it by. Okay, so I'm going to do this. Now what we just need is a Boolean toggle to tell Grasshopper, Ladybug to run the analysis. So just as a recap, this is what we have done. This is what you have learned last week. Now our only next two steps were the sky matrix and the incident radiation. Okay, so if you are all set, just double click on the toggle and you will be able to see your analysis. Okay, so it's pretty fast. As I've said, it's better to switch off your analysis surface so that it doesn't overlap and distort your view. Okay, you can also go here and hide this preview so that this is much neater as a simulation study. Okay, so now let's see. Okay. We always have to compare. So this kind of makes sense now. Okay, in terms of the whole site for Paya Lebar, our sun is going like this. Okay, if you take a look at our radiation analysis, it's done correctly, but this building is offering some shade to this particular portion. Okay. I cannot stress how important it is, but always double check whatever that you have done your analysis to. Okay, otherwise you'll be rubbish in, rubbish out. A lot of times when I sit for guest critics and I see students having very nice building designs and facades, but sometimes they don't make sense. It can be a very nice continuous parametric component, but certain parts where it's supposed to react correctly to the sun, it's not. It's just very small when it's supposed to be very big and very big when it's supposed to be very small. But the student is too impressed by the way that they can generate the form that they forget that it's the whole point of being able to use this software is to get accurate and efficient response to the climate. Okay, so now that we have checked this, everything is okay. The next step is what I was sharing earlier on, the north arrow. Because north arrow orientation, all of this is very important. I'm going to move this down just a bit so that I have enough space to do my north arrow orientation. If you zoom down back here, you can see that we have the sky matrix. Okay, I want to be able to set the north arrow here. So I'm going to double click, and then I will put in my north arrow. And if you remember from the previous lesson, let me just take a look at this in the top view. You can see this is Y. Y is oriented to the pseudo north orientation of the 3D model in Rhino. Okay, so now I'm going to move back to perspective view. So for this Y, I want to be able to rotate my vector. Okay, so you have to use this command, rotate a vector around an axis. Okay, there are a couple of rotation commands. Make sure to use this one, where you will have the original vector to rotate, and then the axis. So obviously, my axis, if this is the Y, if I draw it 3D, this is my Z. So I'm trying to rotate it in this manner. Okay, Grasshopper always rotates counterclockwise. You will see that later on. So I'm just going to create I'm just going to move this up. Z vector here. And then the angle. If you hover over here, you will notice that it always rotates in radians. So we have to have a converter. So click on radians, RAD. So you'll convert your degree that you want into radians. So it should be, of course, 0 to 359. Connect this over here. And then now you will have your rotation. Okay, so your vector is rotated. But this vector is like a direction, right? We need to show this onto the Rhino viewports. So to do that, we will use the vector display, EX. So what this needs is a point. I've already modeled a point here, if you all have not noticed. So I need to create a point container. So I'm going to right click, set one point, choose this point over here. And now I'm going to connect this here. Okay. The next step is I'm going to connect this vector. And I can choose what color and width I want it to be. Okay. So maybe I want the color swatch. I can set my color swatch here. And I can change it to whatever color that I want. Okay. And also whatever thickness that I want. Okay. So now you see your little arrow here. So it's a bit short, right? Because by default it's like 1 meter. So how do we change that? So what we can do is I'm just gonna move this out a bit. Okay, something like this. Remember, vectors can be given an amplitude. That's what we learned in the lesson for the esplanade. So I'm going to connect my vector now here. And I can choose my amplitude, how long I want my arrow to be. Maybe 1 to 10 meters. And I'm gonna plug this in now here to replace this. Shift this here. Now if I stretch this, wait, visualizing correctly. 10. Yeah, 10 should do the trick. Rotate the vector. Is this unit too small? Oh, oh yeah, it's too small. Okay. Okay, let's just scroll this down now. Maybe it was so thin. Okay, let me delete this. It should have, oh, 5 is also too big. Maybe 2, 5. Okay, yes. Yes, nice and thick. Okay, so this is my north arrow. Okay, I can hide this. And I'm going to plug my rotated vector over here down to the north. Okay, so now there will be a direct relation between my north and also to the radiation analysis. See, as I'm panning through, see now this is rotated. So say, for example, my north is here now. Oops. Okay. North is like this, and you check. Even my dome is oriented correctly, and this block is significantly changing this building over here. Okay. And the interesting thing is now, okay, this is so we have completed the exercise for here. So you have learned how to do this from scratch. As I was telling all the class, right? So essentially out of maybe 10 students, 5 will probably just use the definition to do their designs. And maybe another 3 will try to figure out how to do it by themselves. And the remaining 2 will be the ones who will try to make this even better. Okay, so that's why we show you how to do this by scratch, from scratch. If you have another building context, okay, so say for example, I'm going to create new layer, 2 new layers. So one is side context 2, and then this is the analysis surface 2. Okay, I can always build very rapidly with a new site using this box tool. So you can just try it out by yourself, something like this. Now that I'm happy, I'll change this layer to the analysis surface here, and I'll create a surface here. Okay. I'm going to create my surface in a clockwise manner, which will create an error later on, so that you will know how to reuse this correctly next time. Okay. What I can do, right, is I can just take the whole definition that I've created, Control C, Control V. Okay, so this is my other definition. I'll zoom in here, I right click, set one surface, this is my analysis surface. And then right click. Oh, you can see that it has immediately done the analysis because I've set it to be true, right? And I've hidden my surface in the Rhino viewport so that it doesn't look so messy. And you can see here, it doesn't really have a lot of sun, right? Because our context, as in it has a lot of sun here, and it's not affected by these buildings because the context is still using the original context over here. Okay. And then I right click, set multiple B-reps, and then I will choose this ones. Okay. So somehow this still looks like it's correct, but actually it's not, because this particular surface now is not in the correct orientation. So we should have flipped it, because what was happening just now, when you see here, after I flipped it, the analysis is more correct. It shouldn't be yellow throughout. Okay, sometimes it will be blue throughout. Because when you model a surface, there's a, draw this. There's an orientation of the normals. Okay, so just now, the normals was going downwards. So when it's going downwards, it's not receiving it's not calculating the sun which is coming up from the top. That's why we have this issue. Okay. So move this to the side. So that's what I mean, and that's why I purposely do it like this, so that you all know and you all won't make the same mistake. Or if you do still make the same mistake, then at least you know how to fix it. Okay. And the next thing is, this is, you can do this to any other site. So for example, say we are going to choose somewhere else, like maybe in Denmark, in a northern hemisphere. So copy link to clipboard, double click here, and paste it over. Okay, so now you can see that the solar radiation values are significantly less, right? I'm just going to see, I have a point here. So it's overlapping two of this. This is still doing it for Singapore, right? And it's showing the original one from here. So what I can do is I create another point, and then I will right click, set one point for this guy. It's too close. Let's pull this down a bit. Okay, so these are two sides, right? Or not to forget, I should also set, oops, because I hit this. I will move this down. And then hide this again. And then remember to change the point to set 1 point here. Okay, so this is how our radiation analysis is. You can compare between these two sites. Okay, Singapore, Paya Lebar versus Copenhagen. Okay, maybe just to make it easier, I will change all of the north to be the standard north. Okay, so you can see from here that this really truly reflects actual circumstances, right? The north is, as in, because the sun, the earth is round. Okay. Sorry, this is too big. I think I better sketch with this. Okay. So this is the sun. This is earth, and then this is the sun. Right. So because the earth is actually tilted at an angle, right? So if this is Copenhagen, it is when the sun is shining at it, it's taking in the sun more from the south, whereas Singapore is very near the equator, on the equator. So it's generally taking it right smack in the middle, as our Earth also orbits around this. Okay, I'm gonna close this. Now I'm gonna delete this. Okay, so all this is very useful for you because it's already formatted nicely. You can just screenshot and put it into your analysis panels, part of your design studio, or even if you don't want to do it, you are more towards the the material studies or the history studies, then but at least you know where is the orientation so that you can put your spaces to maximize daylight illumination, right? So this is a very useful tool for all of you to use. We will stop here for now. We'll have a break until 10 o'clock. And then, yeah, if you have any questions, feel free to raise them, especially those online. Once we come back, so make sure that you rest well during these 15 minutes, because once we come back, we are going to have more intense lesson later on, because we're going to apply these radiation values to influence the way in which we have set up the Esplanade sunshade. So there will be an inverse relationship between the heights of the sunshade versus the amount of radiation that the sun falls on, because we want to keep the sun out. for our context in Singapore. Okay. So let me put this in. Lab got how many people? So sad. Nobody. Oh. Later I can continue. You think a lot of them like, go for the web. But it's supposed to be speech. Okay, just nice, 10 o'clock. Let's continue. Okay, so what we have left off is analysis, and okay, let me just group this together so that you can see the difference. And then this is the one on top. Okay, so just now we spoke about the analysis period. So this is done by setting it to the HOYS over here, hour of year for the sky matrix. So to create an analysis period, you can just double click and type analysis period, and you'll be here, LB analysis period. So if you were to just put this in here, it will still do everything because by default, it was set for the entire period. Okay, so what you need to do is, let me just move this to the side so I have more space. So it needs the start month. So you can set your slider to be 1 to 12, January to December, start day 1 to 31, and then start hour, end month, end day. So you can be very specific. You can set it like from 0 to 23. So this will be the 3 values that you set up. You can duplicate this, and that will be the end month, end day, and end hour. Okay, for all of this. So I'm just going to put it, say, for example, at a specific day. Okay, so maybe 6. So in June, okay, for midnight is okay. And then to June to the next day. So just 1 day difference. So as I'm plugging this in here, you can see that it's already updating itself, but it's going to do it for half a year. Okay, now it has set to June. Yep. Okay, all the way until here. So then this will be for the full day between these time periods. Okay, so let's move on. I would like all of you to go to here, radiation analysis, radiation.gh. So if you to open this file, you'll find similar to what we have developed just now up to this point. Okay, there is a north arrow, there's an analysis. And then what is different, let me just maximize this, is this portion here. This portion, if you recall, this is where we have created the esplanade sunshade. We took the vertices and then we split them, identified the 4 points, created the guidelines, created the halfway line, and then orientate them and move and orientate them by getting the normal using the cross product and then moving the panel up. Okay. So what is additional here now is how we want to make sure that the panels are similar. Okay, because if you take a look here, the analysis grid that we are setting, right, as a prescriptive number has to be the same as, has to be calculated to make the same amount of analysis results as per my Esplanade sunshade. Okay, so I'm going to go to my perspective view now. Okay, so you can see that this is my Esplanade sunshade. All these radiation panel values here must directly should directly correspond to the number of sunshades that we have. Okay, otherwise, what Grasshopper will automatically do is it will make the last value that was calculated. So in this case, if I go back to my Grasshopper, I know that my sunshade, there are 117 of them, of pairs of sunshade. But my analysis grid now is only 108, those points in which we have analyzed. Okay, this is a mathematical thing. You cannot squeeze this in, right? So, but what we can do is we can use this tool called the interpolate tool to be able to manage the data such that it will create and grow the list from its original 108 value. So it's kind of like creating a mean gradient out of it, so that the result is also kind of correct, but not exactly correct. Okay, so if you were to ask me as a teacher, you should do it apple to apple. So if you want to create 117 sunshade panels, then you have to make sure that your analysis grid is 117. Okay. For this case, this is to tell you what is the backup plan, because by right, most students, they will be happy with this result. Okay. In general, it looks correct, right? So where it's blue here, the sunshade is opening it up a lot. Where it's very hot here, the sunshade is just slightly up. Okay. But what they don't notice, but what I will notice if I go to the gas grids, is you see here, all of these are the same value. Even though it's supposed to be very dark here. Why? Because what Grasshopper will automatically do, if there's 108 values only, it will take the 108th value and replicate it for all of the ones behind. So for the 109, 110, 11, all the way until 117 panel, it will take the value for the 108, which is not correct. Okay. So to fix this, you have to use this longest list tool, where you can right click and then you choose interpolate. Then now this will generally be correct. Okay, but of course not super correct. Okay. Because you can see from the values that I have indicated here. See, this is 3863. This is 3729. So 3863 is supposed to be hotter than here. But this is shorter than here. But at least generally it still looks okay. You get what I mean? So this is like a compromise. a fast fix if you have no time and you need to get this out very quickly. Okay, and also why I want to show you this, so that at least you know how to manage data, which we will come to after the term break when we start to talk about Python and other stuff like that. Okay, so how do we go about doing this? Okay, I will not, I will spend more time trying to explain this to you rather than to do this from scratch. Okay, because I think it's more important for you to understand how this system works rather than how, and you have to practice how to do it by yourself later on. Okay, so you can see over here, firstly, we still have the standard analysis grid size here, right? That is plugged into the incident radiation. That's what we just did before the break. Okay. And those values here are to check the number of midpoints there are, which will obviously be the number of pairs of sunshades that we have, versus the least length of the analysis, okay, the results. So as of now, just now you saw my analysis grid was 3, and I'll have 117 pairs of sunshades and 108 values. But if I were to switch this to say 2, okay, now my grid is finer. I take a look over here. They actually match because it's just mathematics. Okay. And how is it that it matches? How did we set it up? So if I prescribe this to be 2, what happens is that I'm bringing this in to divide the length of each of these, of my surface of my roof. Okay, I'm going to use this button now, this green pill here, that will hide whatever grasshopper geometry that we have. Okay, I will still be able to see this because of the fact that it is doing a custom preview here. Okay, so what I'm going to do is I'll just disenable this first. So all of this will not be created. And same thing as the pipes. Okay. Now I go back to my definition here. So what I've done is, okay, this was my roof. Okay. And in one of the very first few lessons, I show you how to do a deconstruct BREP, right? So deconstruct BREP allows you to get the faces, which in this case is this guy here, or the edges. So the edges would be this, and this. So the way that this surface was created, the edges are actually named as this, and this, and this, and this, numbered in such a way. Okay. So I used the same technique, which was the list item, to focus onto this particular curve, and then also this particular curve. So this is curve 0, and this is curve 1, which are actually conversely the U and the V values. Okay. So by focusing on this, I will get the length of these two curves. In this case, you see if I hover over here, the U or the 0 curve is at 38.5 meters. And the V or curve 1 is at 28.3 meters. So mathematically, you can sort of understand why we will get different values, right? Because if it's divided by 3, as earlier on, doing an integer division, it will have a different result. 38 divided by 3 is kind of like 13, right? But if it's 38 divided by 2 is 19, it's more precise. And then similarly, for this 28 divided by 2 is 14. So 19 times 14 will result in having the 266 values. Okay, so we use integer division so that we end up having a integer value. And this is then assigned to subdivide the original surface into this isotrim. Okay, and then after that, you use the same technique that we have done for the esplanade and to create all the normals for the sunshade. Now, this portion, as I mentioned, is to check the data. Okay, and then now this portion is where you will be able to grow the data. So how do you get this particular command? You just have to double click and type longest list. Okay, so what this does is I'm just going to use a panel first to see what kind of data we are taking in from here. Okay, this is the panel. Okay, let me show you one trick, okay? This information, right, is coming from far, far away, correct? Sometimes when you open your friend's file or you open your colleague's file, it's very annoying to go and find it. So what has happened, what a trick is to just double click on this connection, this curve, this squiggly thing, and it will create a relay. So from there, right, you can transfer and put it to what you want to do next. You don't have to go and find the original connection. Okay, so this is the smart way of doing these things. Okay, as you notice now, as you notice, my entire course, I'm just teaching you how to do it in the fastest way possible, not the most tedious way. Okay, so what is happening here, as you can see from the panel, are all the x, y, z values of the midpoints in the subdivided isotrims, subsurfaces. Okay, so it has all of this information. So it's under list A. Okay, I will create another panel and I'll show you what is happening here. So list A is having all of these panels. Still the same information, all still the XYZ. Now let's check what is the list B information. So I create a relay again, and then I'm going to connect this here. Oops, sorry. And I will connect it to a panel so that you can see what's going on. Right. So here, these are my panel information. Okay. And if I scroll down, see, there's 265 values. Similarly, for here, there is 265 values. Let me just go back and change this now, the grid, right, to 3. Because 2, we have already known that the information doesn't need to grow, correct? Because it's 266 by 266 values. See, I hover over here, you can see that it's creating 266 values. big value. Okay. So now, if I were to change this to 3, okay, and then I pan back here, and then I hover here, this is now 117. And then to this guy here, this is 108. Okay, so now they are different. Okay. So when I hover over here, adjusted list A is still 117. And then this one, adjusted list B and adjusted list B is still empty as of now. Okay, I'm going to plug this in now here. Okay. And then what is happening here is that now we have 108 values here. Okay. And here, these are all the adjusted values with the repeat last. Okay. So similarly, that you see here, this is under this. But if you notice, right, here, you see 1, 2, 6, 3, 6 locally defined values. Why is that so? Because now, in terms of the data tree structure here, see all of this information here is stored in a grid into a tree. I briefly talked about it before, but I'm just going to show you again what's the difference. There is a data branch. This branch was originally the branch from the subsurface. And the subsurface, you have created tree information. Tree meaning 1, 2, 3, 3, not the data tree, which are the faces, edges, and the vertices. So this will create a database in which Grasshopper stores the information. Okay, so when you try to do this longest list, it will extrapolate for every 4 matrices here. That's why you end up having to have 12,636 information. Okay, but now if say for example over here, okay, I cannot flatten this. Yeah, I cannot flatten this. So I just have to flatten it from here. Okay, I'm just going to put this back here. So you can see this is still the same data tree information, right? If I were to right click now and I flatten this information, okay, you can see now that there's only one specific list in a branch. Okay, and then the output here, if I were to scroll down, will be to 116 now. So effectively, this has grown the values to be 116. Okay, but the difference is that now it's still repeating the last 8 values. Last 9 values. See, from 107 onwards. Sorry, let me make it bigger. It's all the same values here. Okay. Now, how can we fix this? So as I mentioned, if you were to right click and now you choose interpolate. Okay, so what this does is it's kind of interpolating all the information and approximating them. So you will have noticed by now that these values from 107 to 116 are not consistent. They are sort of like a approximation of the original relationship. Of course, you see here at the end is a repeated value, right? So all in all, what I've just illustrated to you is how you should understand the information that is coursing through all of these squiggly lines, how to make sure that you always double check your work to make sure that it's consistent with what you want to achieve. Ideally, you should always have the same information here to control. So it's apple to apple for your information that will drive your geometry, failing which, if it is mathematically impossible, then you should be aware and privy to the fact that you can use this tool called the longest list to then interpolate the information so that it gets the best approximation for your intended design. Okay, so this is all there was here. Okay, and the cool thing is, you see right now, after I have deleted those relays, it doesn't really affect the rest of my definition. The connections are still kept. Okay, so this is a good way in which you can, like, sometimes when you download sample Grasshopper definitions from the web and you want to play around with it, or your friend pass you some things and you want to figure things out, this is an important way to troubleshoot. Okay, so now this first portion was to talk about how you make sure that it's apple to apple. Then we're going to talk about how we can make the information logical for fabrication. So in the very first lesson of the Esplanade Sunshade, we shared with you how to use the amplitude as a slider to directly change the height of the Esplanade Sunshade. Then after that, we use an attractor point, remember? So the attractor point will measure, at that point of time, the attractor point will measure the distance from the point to your midpoint, and then use this height for the height of the sunshade. But we realized that when we do that, that means the height of the sunshade will be too high because maybe it's 10 meters away from it. And then this will result in the fact that you will have a 10-meter tall sunshade. And our quick fix to that particular problem back then was to use a division to make it like divide by 10, so that something that is 6 meters away will have a result of a 0.6 meter tall sunshade. Okay. Now, a more elegant way to do this, right, is say, for example, you know that you want to restrict all of this information to a particular domain. Okay, so just to repeat to you all again, you remember when I taught you all how to do a sub isotrim, you have to construct you have to divide domain 2, which is to divide domain square, means you have two domains. in the in the U and the V mapping. Okay, so that was actually mathematically telling the computer, right? This surface, I want to divide it from, say, 0. If I were to just take this as an example. Yeah, this U and V, right? So from 0 to 13, and then from 0 to 9. Because to the computer, they are just counting from 0 to 9, and then 0 to 13. 0 to 13. So, having said that, right, what we want to achieve now is a single domain. So it's not a two-dimensional domain, it's just a single domain, right? And first, we need to know what was the original set of numbers, right? Just now, I was giving you an analogy of how the point is 6 meters away from our panel. Now, our information, let me again use the panel here to illustrate to you. These are all the values of my radiation analysis. So it ranges from 400, say, to like 1,000 plus, right? 1,004. Because just now when we were doing the radiation dome, we knew that Singapore's radiation is around like close to 1,800. So this is the domain that we have. A domain will therefore mean that the minimum and the maximum number. So how do we understand this? How do we create this domain? We will use this tool called the bounds, right? Double click and type bounds. So you put in whatever numbers that you have. And let me just have a panel to illustrate this. It will automatically tell you where the minimum value of this is to the maximum value. Okay, so now we know these ranges of values that are being output from here, which we should not directly put into our sunshade, correct? And then, so this is the confusing part, right? You also have to remember that we don't want a reciprocal relationship. Last time, wherever the point is, it will measure the distance and it will be the height. So when it's closer to it, the height will be smaller, correct? Now, what we are trying to achieve is where the value of the radiation is high, I want my sunshade to be smaller. So that means I have to do this little mathematical operation here where I have to create inverse relationship, right? I have to 1 divided by the radiation values. But if I if I create 1 divided by the original radiation value, which is between 400 and 1,004, then I will get a super small number, right? It will be like 0.00001. So that doesn't make sense, right? So that's why here I'm going to create a domain, a new domain, which I think will definitely work. Okay, so it's again mathematics, right? So 1 divided by 0.3, right, equals to 3. Okay, so this is the end result. 1 divided by 2, of course, equals to 0.5. Okay, so no matter what, all of my sunshades will be from 0.5 meter tall, minimum, to 3 meters tall. Okay, and what this particular, what happened? And what this particular command does, remap numbers, is that it will take let me just create this remap numbers. You will take all these values from the original input, right? Which you can see here. Let me create a relay for you to see. All these are the values that are coming in from here, from the radiation analysis, right? So you take all those values and then you will have to create two domains. So the source domain will be the minimum and maximum of all those values earlier on. And then the target values, which is my 0.3 to 2.0. And then you will create all of this information here. Okay, and all of these values now, if you zoom in, it will definitely be for between 0.3 here, the smallest number here, all the way maximum will be to 2, which will be somewhere, yeah, close to the middle. Yeah, this 1.8 over here. Okay. So there's a lot of values there. Maybe now let me just manually do this, right? Okay, I'm going to key in some random numbers just to test it out for you. I'll create a panel. Okay, so I can just type. So all of these numbers are not to a particular order, right? Okay. I have to right click and make it a multi-line data so that it knows that it's individual data. Otherwise, it will think that it's continuous. Okay, so I have these 7 values here. Okay, so this is my value. And then I also want to know what is the bounds of this. So I double click and create the bounds. Right, and then let me just check what are my bounds before I plug it into the source. So this is from 7 to 648. Let me just zoom this out. Okay, so it's from 7 to 648. I can clear that annotation. Okay, and now I want to create a target. So I want my target to say be from. So I will have to construct a domain. So construct a simple domain here where I need to have the start and the end. So maybe my start will be from 0.1 to 2. Okay, so I will duplicate this and then I just check. Okay, so this is my domain. So 1 is from 0.1 to 2 over here at the bottom, and the original one is 7 to 648. Okay. So my source will be this particular bounds. All of this information, the minimum and maximum, and then this is my new target, which will be from 0.1 to 2. Okay, I know for sure there are 8 values here because from 0 to 7 means 8. Now I'm just going to show you what will happen. So you can see from here now, I have 7 values here, right? And they are ranging not less than 0.1. 0.1 is the minimum, all the way until 2. So you can identify it very clearly here. You can see that the smallest number here, 1. Wait, let me just use a red color. Okay. So this is 0.1. And it's at index 3, right? Index 3 here. So this is correct because the smallest number here in this original list was 7, right? And then here in the remap value, the smallest number is equals to my target domain, 0.1. Now I'm going to see my maximum value. Okay, so the output maximum value here is 2 at index 5. Let's see from my original set of values. So yes, this is where the maximum was, 648. Okay, so everything else, it has done a mathematical operation to extrapolate that particular number to be a relationship from here to here. So 11, as a relationship of it from the minimum and maximum value, will result in a remapped number to be 0.11856. Okay, so now all of you are clear what is happening. And so this is how we will be able to take all of this information, all these remap values, divide them, and then just plug it to the amplitude here to create the end result, which will be your sunshade here. Okay. So now you understand. Now, you will understand this is the important thing to take away from today's lesson, which is to make sure. Okay, let me summarize again. Make sure that you always check that your information is apple to apple. Okay, if it's apple to apple, then that's good. Otherwise, you will have to grow the data. And lastly, the most important step actually is to always use your human mind to go and see whether or not the information is correct. Like just now, the first example, even though you can see that there is some radiation analysis, the color is yellow, but it's not correct as per the sky dome that we have on the right-hand side. For this. Okay. When this panel was flipped. See, it's kind of look correct, right? There's some kind of analysis, but it doesn't really correspond to the actual radiation analysis here. Hey. So we have come to the end for today. You can feel free to type in your questions. Okay. While you're thinking about your questions, I will tell you all about next week. So next week will be about butterfly. Okay, I can expect pandemonium because butterfly, right? The open foam installation is firstly, it's quite hard to install it properly. Secondly is most of the setting, I have prepared a set of files that has dumbed down the radiation analysis to 1 million points instead of 2 million points. But even that is quite taxing on most laptops. Usually when we run flow simulations, we will do it on a desktop. So I think for next week, most importantly, we will spend like half of the time trying to make sure that all of you have the installation done correctly, right? Then we will just show you a simple walkthrough of the example file of where there's only 2 buildings, right? With 1 million points and at a more cost definition of the meshing. Okay, because when I tried the butterfly again, it took me 14 hours to do the simulation, okay, on a normal desktop. Okay, so yeah, so that's it. So make sure to have your laptops all fully charged when you come next week, or if you're at home, then it's okay. If you're at home, try to do next week's lesson on a desktop if you do have a desktop. Yep. I will post the installation examples on this on the canvas, but it will be more interesting. I think next week I will take one person's laptop and install it there on the spot for that person. Then you all know how to install it properly as a demonstration. Because mine is all fully installed for most of my computers. Okay, so no further questions. Are we allowed to consult you for the submission next week? Yes, you can email me and any of the TAs for your date, for your session. So Friday session, we have our 2 TAs. No, we have 4 TAs. Yes, 2 in the lab and 2 in the LT. Yes. You can feel free to consult me or the TAs. My email is in yeah, since we have some time, I show you. I have already uploaded the sample assignment file that I have shown you before. I don't know, but okay, I just showed. It's with much, right? Yeah. Never mind. They want to do faster, it's okay. Can even better. Okay, so this is the one that we have discussed. So the sequence is how the definition is deconstructed and built. So this will correspond to what is happening in your definition, what is controlling it and what is the output, and then illustrate how the 3 parameters will affect your geometry and how this can be applied on 3 different surfaces. Okay, I have also put in like that is me doing it from deconstructed way. I've also found from Pinterest, right, this good example of how this particular person have tried to explain his grasshopper definition, right? So this is what each of the definition is doing, and then this is the different parameters, and then the end result. Okay, very nice and neat. There are a couple of other examples that you can always feel free to go and take a look. But yes, this is the expectation. Okay. Okay, wait, any other question? Okay. So if no questions, I will end the meeting for all.